All right, now that we've kind of taken a look at how to pick samples, how we pick a group from the population to collect data from, we want to kind of start looking at what we do with that data. So we're going to start by kind of talking about two very important things in statistics, and that's the parameter and a statistic. Now, most people just think of everything as a statistic. So if I say 1 out of 5 people chew gum, maybe once a week or something. So most people will say that's a statistic, but there actually is a difference whether that is what's called a statistic or a parameter. Now, a parameter is going to be a value that is true of the whole population. So everybody that you're talking about, if the value is for the whole population, we call it a parameter. A statistic is going to be a value that is true of a sample. So when I say 1 out of 5 people chew gum, does it mean that I surveyed 5 people and one of them chewed gum? Or if I survey everyone in the population, say it's everyone in America, on average, do 1 out of 5 of them chew gum? So that's a real question we have to start looking at when we look at studies and things like that. So one thing that we will say is parameters are very difficult to find. It's very hard to ask everyone in the population some characteristic. Do you chew gum? How many hours a week do you work? How much money do you make? Anything like that. But a sample is very, very easy. So when we say how will we estimate a parameter, we will generally use the sample to estimate the parameter. Now, there's a little bit more to it, and we'll see that today. But we don't just say, if 20% of some people I talk about did something, then do we say 20% of the whole population? It'll be a little bit more involved in that. Okay? So our first kind of statistic we're going to talk about in this class is what is called p-hat. So p-hat is just a symbol. It's a little p with a little hat on top of it. And p-hat is just going to be what's called the sample proportion, okay? Sample proportion. So a sample proportion is just basically how many out of how many. So if you look at this little formula, p-hat is the number of successes in the sample over the total number of observations. So let's say I asked 50 people if they drove more than 20 miles to get here. So 50 would be my total. This is my total number of people I asked. And let's say that 15 took over 20 minutes. So this is our actual value. How many had that characteristic? So very, very simple. So let's go ahead and look at an example here that has a p-hat. So this one is about a proportion of adults who favor a constitutional amendment about marriage. And what it says we talked to 2,527 adults. These were the number of adults that we talked about. And of those, it said that 1,289 were in one favor of this amendment. Now, in this idea, the p-hat is simply going to be the number of people who were in favor of this amendment over the total number of people. So this is my p-hat, 1289 out of 2527, which is 51%. So in general, whenever you have this is how you find your p-hat. So if we have 15 students in our class, and let's say that 10 of you are in favor of less homework, then our p-hat would be 10 out of 15, which is 2/3, which is 0.67, which is 67%. So we would say 67% of the class is in favor of less homework. Now, depending on your population, that doesn't mean the whole population would feel that way, just this percentage that we have. So here is another example. So we have a random sample of 7,589 Americans found that 4,234 of them were in favor of stricter gun control. What can be said about all Americans? Well, our p-hat is 4234 out of 7589. Now, if we do this as a proportion, we just basically divide the numbers 4234 divided by 7589. I get 0.558 if I round to that. So that's about 55.8%. Now that's the percentage of the sample. Now, what can be said about all Americans? Well, we can estimate that about 55.8% of all Americans are in favor. But that could be very, very wrong. Because we're basing this whole population of Americans on just these 7,589 people. Now, could that be a correct number? Could that work? Well, sure, it could, but it might not. It might be that this sample is just not very representative of the population. So we have to take into consideration where this sample is coming from, and is it really going to be a good representative factor? Now, the reason this is a problem is one of the biggest problems we have is what's called sampling variability. So sampling variability says this. It says that statistics can differ from sample to sample and don't always match the population. So I asked 7,589 random Americans whether they are in favor of stricter gun control, and I got 4,234 that said yes. Now, if I surveyed another 7,589 individuals, would I get exactly 4,234? Probably not. It could be a little higher, it could be a little smaller, but it's probably going to be different. And do we even know if that number matches the population? So this idea of sampling variability, where your sample can be different every time and not necessarily match your parameter, we call that variability. Okay? We don't really like variability. We like to reduce it. So we have a couple ways to do that. So one way to reduce variability to kind of make it match the same parameter is to have a larger sample. So we can demonstrate this with just flipping a coin. So if I flip a coin, the proportion that should come up heads is 50%, because 50% heads, 50% tails. But if we think about this, if I do some number of tosses, so let's say I do 3 out of 10 tosses are heads. That means my p-hat is 0.3. That's almost 20% off, even though I was only off by 2 heads. Now, if I'm off by 3 heads when I flip it 100 times, you'll notice I get 47 out of 100. That's 0.47. If I flip it 1,000 times and get 532 heads, then I'm at 0.532. And you can see as I go up this, I'm getting more and more heads than I should. I've had 7 more, or 3 less, 32 more, 147 more, 912 more than 50%. But if you look at the proportion, as I actually divide these numbers out and get my sample proportion, you'll notice even though I'm getting further away from the theoretical value, these p-hats are actually getting closer to 50%, and that should be the true value. So what you start to notice as n increases, as n goes up, as you sample more and more people, the sample statistic will approach the parameter. So the parameter, the thing that's good for all the population, if you want to do that, we just have to have bigger and bigger and bigger samples. The bigger your sample is, the more of a chunk of the population you have, the closer you're going to be to the actual parameter that holds for that population. Now, when we're using these samples to try to estimate our parameter, we have lots of samples, and we talked about that. But a lot of times when you actually read results about the parameter, they'll be done in what's called an interval notation and include a margin of error. You've probably seen some point in some newspaper, 20% of Americans are voting for this person plus or minus 3%. So if you take 20% plus or minus 3%, that's somewhere between 17 and 23. So we call this 3% the margin of error. Now, whenever you hear margin of error, a lot of times you might hear that that's something you did wrong, but that's not necessarily the case. The margin of error is the error that occurs from sampling variability. So if you remember, sampling variability is just going to be, that each sample is not going to be the same. Each sample you sample is going to be somewhat different. So the fact when you start taking samples, they're not all the same, that actually is what's called the margin of error. Now, margin of error actually has a really, really simple formula. The margin of error can be simply given by the formula 1 over the square root of n, where n is just the total number in the sample. Now, there are definitely more complicated statistical formulas, but the easiest one for the margin of error for a sample proportion is just 1 over the square root of n. So I just take the square root of n, 1 divided by that number, and I will get my estimated margin of error. So if I look at this example, it said they're asking 1,077 adults if you feel about how much you should tax the rich. So in it found 47% said our government should redistribute wealth, heavy taxes on the rich. What's the margin of error? So if you put this in the calculator, you get 0.03. So that's about 3%. So if it said 47% said that that's what they thought, but our margin of error is 3, remember it's 47% plus or minus 3%. So our actual parameter, the actual percentage of everyone, is going to be somewhere between 44 and 50%. So that margin of error is going to expand what range our actual value could be, because we don't know exactly where it is, but we're just trying to estimate it in this range. So the last statement is how we're actually going to express these statements, and we call these a confidence statement. Now, a confidence statement is just a way that we are going to talk about margin of error. So a confidence statement is we're going to state how confident our interval is at containing the parameter. So how confident are we that the interval we got is going to contain the parameter? Okay? That's what we're trying to find. And they all work very, very similar, right? So you can be more and more confident. So if I am 50% confident, I'm not very confident at all. If I'm 90% confident, I'm more confident, but not 100%. If I'm 99% confident, I'm very sure of my results. So if I look at, say, an example down here. So for proportion of populations who were in favor of guaranteed health insurance, the sample proportion was 0.62. Okay? Let's go ahead and say the sample size. Let's say the margin of error. Let's just say the margin of error. I didn't put it in here. Let's say it's 2%. Okay? So our interval is going to be 62% plus or minus 2%, which is somewhere between 60 and 64. Okay? So if I want to say how confident I am, if I want to be 95% confident, I can just say with 95% confidence, the proportion who are in favor of health insurance, guaranteed health insurance, so everyone gets it, is between 60% and 64%. So if I asked everybody, I asked everybody in the population, all Americans, it doesn't really say who our population is, but whatever this population is, if I asked every single person, which would be very difficult, I would estimate that between 60 and 64% of them would be in favor of the guaranteed health insurance. So, am I 100% sure? No, but I am somewhat confident. All right, let's look at one more example. Now, this is kind of put everything together. Said in a recent survey of voters at a local school levy race, a random sample said 189 out of 256 favored the new tax. Write a 95% confidence interval by estimating the margin of error. Okay? So the first thing we have to do is estimate our margin of error, which, remember, we have a formula for. It's 1 over the square root of n, n being our total number of people. So that's 1 over the square root of 256, which is 1 out of 16, because the square root of 256 is 16, I believe. So 1 over the square root of 256 is 0.03. So that's, oops, I missed a 0. 0.063, or 6.3%. Now, our actual p-hat, our actual sample proportion, was 189 out of 256. 189 out of 256 is going to be 0.738, which is 73.8%. So our interval is going to be 73.8%. That's from our p-hat, plus our margin, minus our margin of error, 6.3%. So I'm going to add and subtract those percentages. So 73.8 plus 6.3 is 80.1. So if I add those two numbers, I get 80.1. And if I subtract them, so 73.8 minus 6.3, I get 67.5%. Okay? So what I would say is, with 95% confidence, the proportion of all who are in favor of the tax is somewhere between 67.5% and 80.1%. So we don't know precisely, but we're using the sample to estimate some statement about the whole parameter. So, a couple formulas, a couple ways to estimate our parameter. If you have questions, obviously, please let me know.